Nós somos com o professor Vanderlei Salvador Banhato, coordenador do Centro de Pesquisa em Ótica e Fotônica, que está trazendo os prêmios Nobel aqui para São Carlos. Professor, a importância da vinda deles e o que eles irão abordar?
Bem, a vinda de dois premiados com o Nobel em épocas diferentes, inclusive um que é recente, né? O David Wineland, tem como objetivo a gente fazer uma coleção de palestras mostrando a importância da mecânica quântica para a sociedade de um modo geral, em especial para os estudantes de física e engenharia. As ciências quânticas, que são muito dominadas pelos físicos, passam um momento muito importante de transição do conhecimento para a aplicação. Já está se propondo e já realizando computação quântica, telecomunicação quântica, sensores quânticos que vão ser muito mais sensíveis, vão poder detectar doenças, detectar pragas na lavoura e tudo isso. Então é importante a gente motivar os jovens para que eles se envolvam nessa nova fase de utilizar o conhecimento científico gerado para a solução de problemas da sociedade.
A sua proximidade com o Prêmio Nobel Bill Phillips e também com o David, fala um pouquinho sobre quem são eles para a sociedade entender um pouquinho.
Bom, Bill Phillips ganhou o Prêmio Nobel em 1997. Ele é um Nobel que idealizou a forma da gente remover velocidade de átomos para poder entender melhor a matéria, e isso teve uma consequência enorme. Ele é do National Institute of Standard Technology, NIST, nos Estados Unidos, no estado de Maryland. David Wineland trabalha com íons aprisionados, que é um dos elementos principais nessa nova modernização da computação, né, introduzindo a chamada computação quântica. Também é um cientista que sempre trabalhou com aspectos fundamentais, tá certo? Ele é do Colorado, da cidade de Boulder, e ganhou o Nobel com o francês, com Serge Roche, né, devido à importância que tem observar fenômenos quânticos a nível atômico e deles fazer o melhor uso que a gente pode para a solução de problemas.
Trazendo eles para a USP, o professor pretende então sensibilizar todos os estudantes, comunidade científica em geral, mostrando essas linhas que o professor também trabalha.
Exatamente, não é só sensibilizar, mas é mostrar as perspectivas que temos. Todo mundo é sensível com a ciência, com o desenvolvimento. A questão é que nós precisamos jovens, né, que aceitem o desafio de avançar esse conhecimento, de levar essa ciência para as suas consequências finais, que é realmente dar relevância, não só avançando o conhecimento, mas resolvendo os problemas que a sociedade enfrenta.
Professor, translation please. O que eles vão falar durante a apresentação deles hoje? Só essa pergunta, por favor. O que ele vai abordar na apresentação dele, na palestra dele em si?
So he wanna you to ask what you will present today in your talk, okay, about quantum mechanics. Yeah.
Well, today I'm going to be talking about the quantum reform of the international metric system, the modern metric system. The metric system, the system that everybody uses to measure things, to report the values of what they measure. The metric system began with the French Revolution in the late 18th century, and it's been being improved ever since. And today, we are now seeing the results of what I consider to be the most revolutionary change in the metric system since the French Revolution, where we are using quantum mechanics to define what we mean by a kilogram. So it used to be, just a few years ago, that the definition of the kilogram was that it was the mass of an actual object, a unique object that was kept in a vault outside of Paris. And today we define the kilogram by fixing the value of Planck's constant, the constant that we use to set the scale for quantum phenomena. And so we now have a quantum kilogram, and quantum mechanics figures in the definition of a number of other of the base units of the of the metric system. So I'll be talking about how that works, why we had to do it, and how it's working today.
Okay, thank you, Will. Professor?
Yes. Well, tomorrow I speak, and I'm going to say a little bit about quantum computers. And so this is, as you may have heard the term, but it's an interesting potential way to do certain computations, and in fact, for certain computations, it can be much more efficient than a regular computer. So they don't exist in a useful form yet, but there's a lot of effort. We know the principles, and so we're trying to scale these principles up. So anyway.
E nós seguimos acompanhando aqui a apresentação dos professores e o professor Euclides Marega fará agora uma interposição aqui.
Today I saw the results of a PASI 2022. You know, PASI, it's a OCDE exam in science, math, and reading for, 100 countries in the world. And I see the ranking of all the subjects. And it's very interesting, for us to make a reflection, because the first country in the, European or America is Estonia. All the other ones are all from Asia. And okay, if you think in Brazil in science, reading, and math, we are in one of the bottom line. US, I think, is in the middle, not so close to Asia, but it's in the middle. But it's one thing that we need to reflect, that how we are teaching science, also math, to our kids. So because the next generation will be affected by what we are teaching today. So well, this is one thing that we need to reflect, and thinking about what we want to do, or just what China, Singapore, Korea take over about science and everything in the next 20 years, yes.
One of the things, I don't know if you want to record this or not, but it's not clear whether they sample in the same way, because in a lot of countries, the only children that are going to be taking these exams are the ones who are at the top of the distribution, whereas because of the fact that in a lot of countries they track students into different tracks depending on how they do on exams, whereas in the US they don't do that, and probably in Brazil they don't do that. So it may not be comparing the same things in the different countries.
So I actually don't know this report you're talking about. So
I just read today.
yeah. Uh-huh.
PASI is a OCDE. I think they made they apply the test for, they make some statistics and take into account public schools, private schools, or districts and other, geographic, I don't know how they manage it to make a good statistics. I don't know how they apply this, yes.
But it's not so much the statistics that I was wondering about, but the sampling.
The sampling, yeah.
Yeah, that is, how are you doing the population sampling? Is it a fair representation of all of the students, or only of the best students?
My understanding is they do not only for the best ones, but for the whole country, and the whole population. I don't have details about how they make the sampling,
That
but
would be the thing you'd
yeah.
have to look at that carefully.
Então, dessa forma, a gente continua aqui, tá? E junto com os Prêmios Nobel que estão aqui, acompanhando todos os trabalhos do Centro de Pesquisa em Ótica e Fotônica da USP, aqui no Física. Estamos com vocês. Nos acompanhem.
Queria dar as boas-vindas a vocês. Nós estamos dando início a uma sequência de palestras para comemorar os 100 anos da mecânica quântica. Parece tão distante de todo mundo, mas hoje já é além de estar envolvida no seu celular, no GPS, no NMR que você faz, no hospital, nos sensores, em tudo isso, está virando tecnologia palpável, como é o caso do computador, das comunicações. Então, a ciência deixou de ser boa somente, excelente, para ser relevante. Pretende-se que resolva problemas. Então, a ideia de trazer 2 premiados com o Nobel em mecânica quântica, tópicos relacionados, e envolvido com aquilo que motivou o avanço tecnológico das coisas, é para motivá-los, e precisamos mais gente nessa área, né? Tá certo? E para alertar que ciência não é só para o cientista. O cientista não faz ciência só para ele, né? Ele faz para uma sociedade enorme. Então eu vou rapidamente. Now I'll flip to English. I will do my best. And I know that many of you can understand my English because it's macaronico. And I will explain what we're doing here today. So first of all, the celebration of quantum is already started. We are just coming from the Academy of Vaticano, where they gave a very important kickoff on the direction of show that quantum mechanics is an important concept, even for non-physicists, right? And there will be a very nice statement about that. And I encourage you to get in the homepage of the Vatican Academy of Science and read it, because that was done by more than 50 scientists deeply involved in this field. Okay, so we have, I'm not going to do a formal introduction, because if you type William Phillips or David Weiland, you go directly to the Nobel page, and they describe it much better than I could. Who are those guys? Okay? But maybe I know those guys better than the Nobel Committee. Both of them are good friends of our institute. They used to come here often. David came on the 90s, and Bill is coming basically after I got here, the first year he came. And amazing that they work in different fields, as you can see. And the only paper they have together was done in São Carlos. Right? So it is a good pleasure to have both. They never decline the invitation to come to our institute. And they know the importance to speak to you, more to visit me. Today we have 2 persons, which I'm going to call 2 states. The first state is called David. The second state is called Bill. And you know, one of the main characteristics of quantum science is uncertainty. You came here today to see David, and you're going to end by seeing Bill. This is natural of quantum science. But let me elaborate a little bit. You see, quantum is very famous to superimpose life and death, cats, but we're going to superimpose Bill and David. And after we have done, we found that by lucky, we got a pure state. So Bill, we collapse on you. But don't get disappointed, because the interaction continues. And in the case of Bill and David, the oscillation between being the Bill or being David takes 24 hours. So now that we did a measurement, this is very important. You're laughing, but this is the way we do many things in quantum. Oh, David is going to speak about flipping things by pi phase. We go from Bill to David. If you wait long enough and do another, and then we mix again, we're going to go home, continue the interaction, and then tomorrow, 24 hours, we're going to go back. But we're not going to need to do this measurement again, because now we understand that we made one, and then we let the system evolve again, and then we're going to do a second. And I guarantee to you, tomorrow will be David. So tomorrow we have the talk of David. And this happens in quantum mechanics. We could not tell you exactly who will be the first to speak, because until you start to get in here and people start to prepare, the measurement was not concluded. Now that we collapse in Bill, we connect again and pray God that everything is going to work.
Well, remember, we're going to have questions during the talk. While we were together at the Vatican, I caught a cold, and I'm afraid that my voice hasn't really recovered yet. So I hope that the stress on my voice does not make it too hard for you to understand what I'm saying. I'm also going to apologize because I think that the talk is too long. It took us too long to get the computer working, so maybe I'll try to skip a few things. But anyway, I'm going to talk to you about the revolutionary quantum reform of the metric system. And I'm from a place called the Joint Quantum Institute, which is joint between the National Institute of Standards and Technology and the University of Maryland. And I'm part of the laser cooling and trapping group, of which Gretchen Campbell is the leader. And I want to emphasize again what Vanderlei said, that you should think of questions. And if you ask a question, you will get a prize. And I think I may ask Lucas to give out the prizes, because it's going to be hard to do. We may have to pass the prizes around. Any question is okay, except for what is the prize? So, what is this revolutionary change to the metric system? Well, as people have said over the course of history, that science is about what you can measure. And if we make measurements, we have to express those measurements in some kind of units. And the international community has agreed that we're going to use what we call the metric system, which is known formally as the International System of Units, or the SI. So whenever you hear me say SI, I'm talking about the metric system, the modern metric system. And what I'm going to tell you about today is that recently we have undergone the biggest revolution. Well, first of all, the metric system started during the French Revolution, which was near the end of the 18th century, and we are now experiencing the biggest revolution in the metric system since the French Revolution. And the International System of Units today has 7 base units: the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. And the definitions of all of those units are now based on some constant of nature. That is, we define what we mean by a meter or a kilogram or a second by defining, fixing the value of a constant of nature. Now, to understand how this is possible, I'm going to talk about one of the most important units that we use, the unit of time. And with apologies to Stephen Hawking, I'm going to bring you my version of a short history of time. Since people have started to talk about seconds, the definition of a second was that it was a fraction of a day. A day has 24 hours. There are 60 minutes in an hour, 60 seconds in a minute. So a second is the length of one day divided by 86,400. That seems very easy, very intuitive. The trouble is that for more than 100 years, we have known that the length of the day changes. The tides slow down the rotation of the Earth. Earthquakes, changes in ocean currents, change the angular momentum of the Earth, and that means that the rotation has to change to compensate for that. So we learned this by having clocks that were better than the rotation of the Earth. One of those kinds of clocks is an atomic clock. This is the first atomic clock. It actually used a molecule rather than an atom, an ammonia molecule. In 1949, this first atomic clock was better than the rotation of the Earth. Today we use cesium as the atom that keeps time, and the first cesium clock was made in 1955 in the UK at the National Physical Laboratory. So in 1960, the international community decided they would redefine what the second was. Instead of being a fraction of the mean solar day, the second was going to be something else. And we now had the technology to do much better than the rotation of the Earth. We had atomic timekeeping. For more than a decade, we had atomic clocks that were better than the rotation of the Earth as timekeepers. And so, in 1960...
Então, nós vamos ter a segunda palestra, tá certo? Como eu falei para vocês, nós estamos dando início à comemoração dos 100 anos da mecânica quântica. Vai fazer 100 anos que de Broglie fez a tese dele. Aí depende o país que você está, eles dão um argumento diferente. Aí o outro vai dizer na Áustria que é só daqui 2 anos que o Schrödinger publicou o trabalho dele, aí vai, mas a verdade é que o trabalho do de Broglie foi o mais importante. Em julho nós vamos ter aqui um encontro internacional, Laser Physics, onde vai se dedicar 2 dias só à quântica. E estão convidados já, tá bom? Vai vir muita gente de fora, já confirmado, então aí nós vamos fazer a nossa parte. Okay, so thank you for coming. Today we're going to have the second lecture of this series in commemoration to the quantum mechanics. As I told you yesterday, there is always uncertainty related to quantum mechanics, so we didn't know who would speak yesterday, but then we collapsed Bill. So we knew that Bill was yesterday, and we continue our measurement, and we knew that if we wait 24 hours exactly, we're going to meet David. And here is David. David Weiland is a scientist that has many, many contributions. We all recognize that he gave the seminal ideas of cooling atoms and ions, many, many research in ions. He worked with, I think he's the only guy I know that had as a thesis advisor a Nobel Prize. And there was Norman Ramsey that came here 3 times. And as a postdoc, another Nobel Prize, Hans Demmelt. CAT is a macroscopic object that everybody in quantum mechanics used to demonstrate the principles. And originally they used CAT, dead and alive, and people keep it cats. But could be dogs, could be cows, elephants too big maybe, but could be anything that's macroscopic. So David, please.
Okay. Well, thanks for the nice introduction, Vanderlei, and thanks for all of you to come to the talk here. I first met Vanderlei when he was a graduate student at MIT, so I've known him for a very long time now, and we've had a good relationship ever since, and have visited each other's labs and so on. So anyway, it's a pleasure to be here. So I'm not going to be able to, you won't learn about quantum computers in this talk. There's just too many details, but hopefully I can give you some impression of what goes on and why it might be interesting. So that's my hope here. Okay, so I'm just going to give a bit of a summary about why we want to use quantum states for computers. And I mean, it really brings up a weird situation given by this example of Schrödinger's cat. And I'll say a little bit more about that in a minute. And I'll try to give you some idea how we actually manipulate the quantum states for computers. And I'll come back to this idea of how quantum computers, if we can actually make them, are very, very much like Schrodinger's cat. So one way to talk about superposition, I mean, superposition is a very, very strange concept, but one way, a classical analog, which I think gives a pretty good idea of, is an example I'll show here. So if you consider this box in this picture, at sometimes, you'll tend to view this face here as being in the foreground, whereas sometimes you'll view this face in the foreground. So you tend to see, it depends on how you play with your eyes, but sometimes you'll see one image or the other. And this is, I think, a good idea of the idea of superposition, that this box up here has the properties of both views that you see in the second picture. And so when you tend to see one image or the other, that's a bit like a quantum measurement. We collapse this quantum state represented by the box up into one situation or the other. So the idea is there's this ambiguity about which state our quantum box is in, but it possesses both properties simultaneously. And then a quantum measurement is just what I said. It's the idea of collapsing one into one image or another. It's like collapsing the quantum states. The efficiency of networking for sure. And so, I mean, I don't know the details particularly how they're interested, but it's clear that things would scale up much better in networking. Yeah.
And that would also imply in the way we would deal with communications in the future, probably, right? The way that my son said.
We can think about new communications way in the future.
Well, that's right. I mean, you certainly can think of completely secure communication using the quantum ideas, because you can tell when someone is interfering with the system. So, yeah.
Thank you.
The hackers may not do so well with quantum computing.
Hello. Oh. First of all, thank you for everything. It's been a pleasure and an honor to be here and just listen to you guys, and it gives me shimmer. So, and I'd like to ask why physics, and similarly, you asked. Oh, I forgot about the word, but own thing. Why Bill chose physics, and I'd like to ask you too. Why physics?
Why I chose physics?
You asked Bill yesterday. What was he's asking?
Oh, yeah, yeah. Okay. Well, my story is not very profound. As a young kid, I liked mathematics, and I also liked mechanical things since I was a kid. And so, I saw how mathematics could help describe mechanical systems and other things. And so and because I like mathematics, I was immediately drawn to quantum mechanics. And so it just kind of grew from there. But I didn't, certainly when I was in high school, I didn't think I was going to be a quantum scientist particularly. But,
And David is a very good biker. In Boulder, high altitude, it's not easy. Yeah. Okay, so I know that there are many other people for questions, but we're not going to leave. So I think it's better if you approach and, like yesterday, David can answer the questions. I told you about the quantum paçoquinha, which is wonderful, you should try. But I asked Bill to bring his Nobel medal. And I think many years ago you brought. I remember people putting it everywhere to picture. But then this time he brought some equivalent. So we have here 4 medal, which is very tasty because inside there is chocolate.